So let's continue with where we were talking about the derivative, and in particular, I want to look at how the derivative itself actually defines a new function. And really, when we see how it comes about, it's actually kind of a neat little thing that it gives us a function. And the reason is because the way that we defined the derivative, right? We said that the derivative at x equals a is the limit as b approaches a, f of b minus f of a divided by b minus a. Or if we wanted to talk about the derivative at x, then we can also write this as the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So we have these things. Why did I say at? This is not Star Wars. At x. At x, we have this formula for it, or at a, we have this formula. What you will notice here is that we can specify what value we want a to be, or what value we want x to be. Now, b and h, those we cannot specify because we are taking the limit as b approaches a, or the limit as h approaches 0. So b and h, those are variables that are in there, but they're not variables that we're able to choose or do anything with. They are sort of determined within the definition itself, what they are doing. But what we can do is we can pick a or x, depending upon which way you want to write it here. We can pick this number, and then this limit gives us back a number, or maybe it gives us back undefined, right? There are certainly examples here where this limit might not converge to anything. But the point is that if it does converge, it gives us back a number. 1 second. So, in other words, this does define a function. Because in this case, it's a function of where we choose a. In other words, remember, a function is something that we give it a number and it gives us back a number. Well, that's exactly what's going on here. We give it the location where we want to find the derivative, and it gives us back the derivative as a number. So it is, in fact, a function. In other words, to be very specific, these are functions of a or x, respectively, depending upon which one we want to go with. And what we can say then is, well, what we want to ask, I should say, what do we want to ask about this? Is there a way that we can write down a formula for the derivative in general by using these? And the answer is, yeah, in a lot of cases we can. The reason is because we can take these limits, leaving x or a, depending upon which one of these forms you want to use, we leave that as an unknown. In other words, last time we did these examples where we asked, like, what is the derivative at 4 or at 2? But what if we didn't do that? What if we just said, well, can we find this limit but leave the variable as a variable, as not something that's fixed? And the answer is yes, we can do that in many, many cases. So, for example, if we wanted to find the derivative of f of x equals 3, and when we say find the derivative, we mean find the derivative as a function. So if somebody just says that they want you to find the derivative and they don't say at some particular point, what they want is they want the function that gives you this derivative. So the way that we can do this is we can say, well, let's just take the limit as h goes to 0, f of x plus h minus f of x divided by h, and we will leave the x as a variable. We will not We will not substitute any particular value in for x here. So let's take a look at what happens. Well, in this case, the answer is not a lot, because the thing is, this function is always just equal to 3. So this becomes the limit as h approaches 0 of 3 minus 3 over h. That's the limit as h approaches 0 of 0 over h, and that comes out to be 0. So the answer here is that the derivative of this function is actually just equal to 0. Now, one of the things that we can do is we can actually say, look, there is nothing in this whole procedure that I just did that depends upon this function being equal to 3. So I'm going to change this a little bit, and you'll see that it comes out exactly the same. Let's suppose that instead of having a function that's equal to 3, let's suppose that I just leave my function equal to some k, where k is an unknown constant. Then, what am I going to get? Well, I'm going to do exactly the same procedure. That's why I didn't bother erasing anything here, because I'm doing literally the same thing. I want to show you exactly how similar this is to when we had that specific number up there. The only difference is now I have the limit of k minus k over h, but that's still just the limit as h goes to 0 of 0 over h, and that still comes out to be 0. So actually, what we have established here is that the derivative of any constant function is equal to 0. It's just the 0 function. The function that always returns 0 no matter what. It has no dependence upon x. So that's sort of an interesting result here. And by the way, that is a result that we're going to make use of in the future as one of our rules for taking derivatives. Because eventually what we want to do is we're going to want to try to move away from finding derivatives by calculating limits directly. We're going to start asking things like, are there any particular rules or patterns that we can just use so that if I look at a function, I can compute its derivative without having to actually explicitly mess around with limits. But for now, we're going to keep on using the actual definitions and just kind of plugging away with those to find these things. Now, we're going to go over some more examples of finding the derivative as a function, but first I want to introduce some notation for finding derivatives. Now, there's two basic types of notation that people use when talking about the function, or the derivative as a function, I should say. And one of these is due to Isaac Newton. One of them is due to Leibniz. And both notations have their advantages and disadvantages. That's why we still use both of them to this day. If you go back into the history of this stuff, a lot of the ideas of calculus had actually been studied before Newton and Leibniz, but they were the ones who first kind of fully came up with this kind of universal idea of a derivative. So people had been computing tangent lines using geometric ideas before Newton and Leibniz came along. In fact, they did a lot with computing tangent lines before Newton and Leibniz came along. But they kind of put everything together into this one uniform idea of the derivative. And the thing is, they probably did this work completely independently. But at the time, there was a huge controversy over which one of them invented it first, and also whether one of them ripped the other off. Because there's reasons to think that Leibniz did it and then Newton kind of ripped him off without crediting him. But probably we think that they could just developed it independently. It's just difficult to say, and it wasn't helped by the fact that Newton decided to put together a committee to investigate this and concluded that Leibniz was the plagiarist. And then it came out that Newton was the one who had investigated it himself, and it was a whole mess. So, yeah, all these political things. Fortunately, the mathematics doesn't care about the politics. Mathematics is sort of these abstract facts that are true independently of people messing around politically and things like that. So let's take a look at the two different types of notation. Sorry, that was a long digression about nothing really relevant to the mathematics. So notations for the derivative. The first notation is differential notation. And we write d over dx f of x. And this means take the derivative of this function f of x and give it back as a function. Sometimes this will also be written as df over dx. Now, why does this notation happen? I just want to explain where this notation comes from, because if you just see it, it's a little bit weird. The idea is, think about what is really going on in the limit as h goes to 0, f of x plus h minus f of x divided by h. Well, let's write delta x is equal to h, and let's consider f of x plus h minus f of, I'm sorry, I'm blocking this thing. Let's consider this numerator as delta f. So this is f of x plus h minus f of x. Why would we do this? Well, remember, a capital delta just means change. So this is the change in f, and this is the change in x. And you'll notice that when we look at this limit, yeah, this is the change in f, and h is actually the change in x. So what we are really looking at is the limit as delta x goes to 0 of delta f divided by delta x. This is another way of writing the derivative that we haven't seen yet. The reason I haven't shown you this yet is because although this is a nice compact way of writing it, it's not actually very useful for computing things. To actually compute something, you have to go back and expand what this means into this bigger format here. Otherwise, I mean, I'm not saying you can't compute anything with this, but it's not super easy to just directly, because you got to figure out what in the world is delta f, what in the world is delta x. Well, let's just write it out in this format that does everything we want, and we can use it. So the point is that these two formulas are the same, and delta, which stands for difference, well, the idea behind this is the delta in the limit as it becomes 0, we change the delta into a d. And so this reminds us, this is the difference in f divided by the difference in x, except it's in the limit as those differences go to 0. It's not an actual difference. In fact, when they were first doing this, they thought of these differentials as infinitesimals, and that is an idea that is hard to make very precise, even though you can use it as kind of a, intuitive guide to what's going on. You can just think of these as very, very small numbers. So when the differences get very, very small, that's what's going on. But what does it mean for them to get very, very small? Well, it really means we're taking the limit as the difference goes to 0. Okay, so that is where this differentials notation comes from. And we'll have more to say about differentials later, but that's where that comes from. The other notation that we have is prime notation. And so we just write f prime of x. So the prime symbol is, it honestly just looks like a little apostrophe. In fact, if you're writing this out with text, you just use a little apostrophe, generally speaking, for the prime. And we use the prime to indicate that we are taking the derivative of f. Now, the nice thing about this notation is that it's kind of naturally set up for us to already remember, oh yeah, this is a function of x as well. So in a lot of ways, I feel like this notation is a bit clearer, because df over dx, also sometimes read df by dx, this is a function of x, but there's no of x here in this notation. So both notations are used. We will be using both notations throughout this semester, and you'll see that there are some things that are easier to express in one notation than the other. However, my personal preference tends to go towards using primes rather than using differential notation. However, the notation is not really the point. The point is that I have lost my eraser. Oh, there's the eraser. It was upside down, so I couldn't see it. Anyway, the point is that these are just two different ways to write the derivative as a function. So let's now think about some things that we can say about some sort of basic functions and what their derivatives are as functions. So let's start with finding f prime of x for f of x is equal to, let's say, 2x minus 3. Well, I'm just going to take the limit as h approaches 0 of f of x plus h. That's going to be 2 times x plus h minus 3. And then I have to subtract f of x. Now, you want to be careful when you do this that you are subtracting all of f of x. That's why I'm putting f of x in parentheses here. Because if I don't put it in parentheses, I would be subtracting the 2x, but not subtracting the 3 here. And so that would be a problem. That would obviously throw everything off. We need to make sure we subtract the entire f of x. And then the whole thing is going to be divided by h. So this is going to come out to be the limit as h goes to 0. And as I mentioned in the last lecture, make sure you keep writing this limit. Don't start just dropping your limit symbol at random. We need to be careful about that and make sure we leave the limit notation in there until we've actually taken the limit. So then what is this going to come out to be? Well, this is going to become 2x plus 2h minus 3. And then I'm going to have minus 2x and plus 3, all divided by h. Now, I notice here that the 2x's will cancel. And to keep track of what cancels with what, a trick that I use is I put a little bubble next to the cancellation with a number in it. So like everything with a 1 in it in the bubbles, this is my first cancellation. And then the negative 3 and the positive 3 cancel. That is a second cancellation, so I put a little 2 next to those. In this particular example, that's not maybe super necessary because, well, there's only 2 different cancellations to keep track of. But if you have a lot of things that are canceling at once, it's nice to keep track of what cancels with what. If you just start marking things out, then it's like, wait a second, what canceled with what? Like, we've now got 23 different things marked out. Which collections canceled with which other collections of stuff here? And it really, it makes it easier for somebody to come along and read what I've done here because they can say, ah, yes, all of these went together and these 2 went together. It also makes it easier for you because if you lose track of what you're doing as you start marking things out, and then you're like, oh crap, something's gone wrong, well, then you can go back and you can check which of the cancellations did you do correctly, which one went wrong. So this is not like mathematically necessary, but it is a very convenient trick. Okay, so now we have the limit h goes to 0 of 2h divided by h. The h's cancel. I'm not going to mark anything because there's literally just one cancellation. Now I have the limit of a constant, and the answer is 2. So f prime of x here is just 2. It doesn't actually depend upon x. This is actually what we would expect if you think about it for a minute. The original function is a straight line with a slope of 2. Kind of unsurprisingly, maybe, that straight line with a slope of 2 has a derivative of 2 at every single point. And you'll notice, if you think about this for a bit, and this is something we'll show next week, really, for any straight line, the derivative is always just going to be equal to the slope. I will, for the moment, leave that. If you want to try to think about that on your own, I encourage you to do so. But we'll come back to proving that in general in another lecture or 2. But in the meantime, it's pretty much the same argument as we had here. Let's see if we can work out a slightly more complicated example here. Something a bit more interesting where the derivative is actually not a constant. Now, one of the nice things about the differential notation is that you can write something like this. I can write d over dx, and then I just put the function that I want you to differentiate over to the right. I just put an expression there instead of having to give the function a name. So if you write something like this, you couldn't write this with prime notation, really. I would have to name this function and then say, find the derivative of this function. Like say, this is my g, find g prime. Well, with the differential notation, I can just put d over dx and then put whatever function I want you to differentiate over here. The process of finding a derivative is called differentiating. You can kind of remember this because the derivative is really the difference quotient, the average rate of change thing. So difference, differentiate. So how do we do this? Well, this is going to be the limit as h approaches 0 of x plus h squared minus x squared divided by h. And now this is going to come out to be, again remembering to keep our limit written here, if I expand this, this is going to become x squared plus 2xh plus h squared minus x squared, all divided by h. Now, the x squareds are going to cancel. There's only one cancellation, so I don't bother giving any kind of numbering or anything like that. And everything that remains in the numerator has an h in it, so I can factor that h outside. And I get h times 2x plus h divided by h. Now, these h's are going to cancel with each other. And now I'm left with something that is a polynomial in h. In other words, I can find this limit by evaluating by just plugging in h equals 0, and I end up with 2x. So now we've finally got something that's a bit more interesting than what we saw before. What we see here is that the derivative of x squared is just going to be 2x at any given value of x. Now, let's take a look at how we can use this in practice to answer some questions about x squared. For example, keep in mind what we just found, that another way of writing this is if f of x is equal to x squared, f prime of x is equal to 2x. And now, let's suppose that I want to find the tangent line to y equals x squared. Sorry, that does not look much like a squared. X squared at x equals minus 2 and at x equals positive 2. So I want to find these tangent lines at two different points. From what we did in the previous lecture, what we could do is just find the derivative at each of these points by using the definition. But we've actually already worked out what the derivative is in general, okay? So all I need to do is I can say, well, the slope at x equals negative 2, this is just the derivative evaluated at negative 2. That's 2 times negative 2, which is negative 4. So the slope here is going to be negative 4. And the point is going to be negative 2 comma negative 2 squared, which is equal to negative 2 comma 4. So my tangent line at x equals negative 2 is going to be y minus 4 is equal to negative 4 times x plus 2. And there we go. Now, if we only have to find the tangent line at a single point, then maybe having the derivative as a function doesn't really save us any work. We could have just used the limit definition at x equals negative 2. But because I have the derivative as a function, I can now go through and I can find the tangent line at other points as well without having to do any new work. So for example, I can now say the slope at x equals positive 2, well, this is just going to be 2 times 2, which is 4. The point is, of course, going to be 2 comma 2 squared, which is equal to 2 comma 4. And therefore, the line that I'm going to get is y minus 4 is equal to positive 4 times x minus 2. There we go. So this is going to be the tangent line when x equals positive 2. Let me just make sure I got all the signs correct there. Yes, okay. So now if I wanted to go on, if I wanted to say like what is the tangent at negative 3, I could do that. I would follow exactly the same procedure. So once you have the derivative as a function, you can answer all of these kinds of questions very, very easily without having to really worry about, like, what are we, really, we don't have to recompute limits because we've got this thing written down as a function right off the bat. Let's take a look at a slightly more complicated example here. Let's suppose that I wanted to find the derivative of the square root of x. Now this one's going to be a bit trickier. We take the limit as h approaches 0 of square root of x plus h minus square root of x, all divided by h. Now, what we're going to do to try to handle this is we're going to do a sort of a rationalization, although it's not maybe exactly the way you normally rationalize. What I'm going to do is I'm going to notice that I can multiply the top and the bottom by the conjugate of this numerator. So this is equal to the limit as h goes to 0 of square root of x plus h minus square root of x times square root of x plus h plus square root of x divided by h times square root of x plus h plus the square root of x. Now the reason I want to do this is because when I cross multiply this, square root of x plus h times square root of x plus h is going to give me x plus h. Square root of x plus h times square root of x and negative square root of x times square root of x plus h, those cross terms cancel. Remember, that is the whole point of multiplying something by its conjugate. It's so that the cross terms cancel. So the only other term that survives is going to be negative square root of x times positive square root of x, which gives me a negative x. In the denominator, I still just have h times square root x plus h plus square root of x. The x's cancel. Now I have the limit as h is approaching 0 of h divided by h times square root x plus h plus square root x. Well, the h's cancel now, and at this point, I can find this by evaluation, provided that x is not equal to 0. If x is equal to 0, then this actually becomes undefined because the numerator is now 1, the denominator is going to 0, so at x equals 0, this would be undefined. But as long as x is a positive number, then this is perfectly fine. So this is going to be equal to 1 over square root x plus square root x, which is 1 over 2 times the square root of x. We can also write this, if we want to, as 1/2 x to the minus 1/2. And there is a reason why I want to write it both of these ways, because later on we're going to see this sort of interesting pattern that happens. But yeah, let's just leave it like that for now. Now, one of the things you will notice about this is that in the previous examples, we had functions whose domains were all real numbers and whose derivatives exist at all real numbers. But in this case, the domain of this original guy, and make sure you have this copied down, pause this if you need to, because I'm going to erase it since I don't have much room. The original domain is 0 to infinity, including 0. In other words, x bigger than or equal to 0. But the domain down here of the derivative is 0 up to infinity, not including 0. In other words, x strictly bigger than 0. The derivative doesn't exist at 0 in this case. Actually, if you look at what is going on with the curve y equals square root of x, what's happening here, the square root of x looks like half of a parabola turned on its side. Well, what's happening is that the slope of the tangent line, as we come in towards 0, this thing ends up having a vertical slope at that point. The tangent line would actually be a vertical line. And the only way that that can sort of make sense is, well, the derivative is supposed to be the slope, the change in y over change in x. But for vertical lines, it turns out that the slope cannot be defined, right? That doesn't have a defined slope. So kind of unsurprisingly, the derivative doesn't exist at any point where we end up having a vertical tangent line. So one of the things to notice here is that just because a function is defined at a point doesn't mean its derivative will be defined at that point. And here is what we say. We will say that if f prime of x exists at x equals c, then f is differentiable, and that's how you spell differentiable, at c. So a function is not necessarily differentiable on its whole domain. But the first thing that we can say is that the domain of f prime is a subset of the domain of f. In other words, you cannot have a derivative for a function unless you actually have the function at that point as well. It would not make any sense. That is kind of obvious in some sense. I mean, when you really spend a moment thinking about it, how could we define the derivative if the function itself isn't defined? We can't do it. If you go back to our definition, yeah, the definition requires us to be able to evaluate f at whatever value we're interested in, because we're taking the limit as h goes to 0, but we do need to be able to actually take that f of x as well. So we do need to have the function itself defined. Another thing that we can say is this. If I take a look at the limit as h approaches 0 of f of, let's say, c plus h minus f of c divided by h, if the limit as h goes to 0 of f of c plus h minus f of c is not equal to 0, well, then this limit cannot be defined, because in that case we would have a numerator that's approaching something that's non-zero over a denominator approaching 0, and that's going to mess this whole thing up. The only way that this can be defined is if this limit is actually equal to 0. And one of the things that this shows us is that if f prime of c exists, then the limit as h approaches 0 of f of c plus h minus f of c has to be equal to 0. And as a result, what we can say is f has to be continuous at c. So if a function is differentiable at a point, it's also continuous at that point. One of the things that this means is that if I can show you that a function isn't continuous at a given point, then you automatically know it cannot be differentiated at that point either. Its derivative is undefined at that point. So there's actually quite a bit that could potentially go wrong here for not getting a derivative. If we have a discontinuity in our function, then the derivative isn't defined either. There's other things that can go wrong, however. So far, what we've seen that could go wrong is we can fail to be differentiable, or fails to have a derivative at points which are, first of all, not in the domain of f. So that's the first thing. It's got to be in the domain. It will fail to have a derivative at discontinuities of f, and it also fails to have a derivative at the vertical tangents. So if we ever get a vertical tangent, then technically speaking, the derivative doesn't exist. You might wonder, so can we still talk about the tangent line? Yeah, the answer is yes. And in fact, we can make sense of the tangent line when we use something called parametric equations. Then everything works out nicely for us. But parametric equations don't get covered until calculus 2 here. So vertical tangents, we don't strictly speaking have a derivative, even though we have a tangent line. It's the crucial point is that the tangent line is vertical. Now, if you have a discontinuity or it's not in the domain, then you don't even have a tangent line. There is another thing that can happen that can mess up having a derivative, though, and that is you can have corners. That's not how you spell corners. Or cusps. So if you have a corner or a cusp, and in a graph, what that's going to look like is it's going to look something like this, or maybe it looks like this. Those are the kinds of things I'm talking about. Sharp points, those mess with whether or not you have a derivative. And one way to kind of see that that is going to not have a derivative here is to kind of notice that what happens in these kinds of cases. Well, first of all, what would the tangent line mean in these cases? The problem is that we're sort of making this instant turning. Like if I'm walking along this curve, when I get to this point, without moving, I have to completely rotate myself around. So I'm not just facing in one single direction at this point. I actually go through a range of directions here. And so there is no intuitive notion of what the tangent line would mean. And that is reflected in the fact that the derivative doesn't exist. As an example of this kind of fourth thing, let's take a look at finding the derivative of the absolute value of x. Now we're going to find this derivative as a function, and we will see that it doesn't end up being defined at 0. So here's what we're going to do. We're going to use the fact that the absolute value of x is equal to x for x bigger than or equal to 0 and negative x for x less than 0. So if x is bigger than 0, then the derivative of the absolute value of x is just going to be the derivative of x, because notice that the derivative doesn't depend upon the function in general. It only depends upon the function in some small open interval around the point we're interested in. That's because we're taking the limit as h approaches 0. So we can ignore everything that happens except for very small values of h. And of course, this is going to be the limit as h goes to 0 of x plus h minus x divided by h. The x's cancel, h over h leaves me with 1, and this comes out to be 1. If x is less than 0, then the derivative of absolute value of x is the derivative of negative x. That's going to be the limit as h approaches 0 of negative x minus h plus x divided by h. The x's cancel, h's cancel, and leave me with a negative 1, so we get negative 1. Not really that much different than stuff we've done before. However, what happens at 0? Well, at 0, we're going to have to deal with the two-sided limits, or rather, we need to do the two one-sided limits, I should say. So, at x equals 0, the limit as h approaches 0 from the right, absolute value of x plus h minus absolute value of x divided by h. For positive values of h, this is going to just be, well, in fact, in general, we're going to be replacing the x with 0. So we're going to have the limit as h approaches 0 from the right, absolute value of h minus 0 divided by h. But in this case, the absolute value of h is just h. So this is h over h, which is 1. But what happens if I look at the absolute value? What happens if I look at the limit from the left? Well, I'm going to encourage you, take a moment to actually think about what this would be and see if you can work it out. And now I'm going to show you, if we take the limit as h approaches 0 from the left, absolute value of x plus h minus absolute value of x divided by h. Okay, we can replace x with 0, so this is really the limit as h goes to 0 from, why did I write from the right? I meant to write from the left, there we go. Limit as h goes to 0 from the left, absolute value of h divided by h. The problem is, for negative h, absolute value of h is actually going to be negative h. So this is the limit as h goes to 0, negative h over h, and this comes out to be negative 1. So what we see is that the left-hand limit and the right-hand limit don't agree. They both exist, but they don't agree. And this kind of makes sense if you look at what's going on with the absolute value function, right? It has this kind of a shape. So if I'm looking at secants, over to the left, all of my secants have a slope of negative 1. Over to the right, all of my secants have a slope of positive 1. They don't come in towards the same thing on both sides. And so what we see is that the limit as h approaches 0 of absolute value of h divided by h does not exist. It is undefined entirely, in fact. So what can we say about the derivative here? Well, the derivative in general of this absolute value, this is going to be a piecewise defined function. It will be equal to positive 1 when x is bigger than 0 and negative 1 when x is less than 0. And there we go. We found our derivative. All right, so I'm going to give you one more thing to think about here today. And then next time what we're going to do is we're going to take a look at sort of comparing graphs and their derivatives, like a graph of a function and a graph of the derivative, and recognizing that sort of thing. But I do want to just give you one more thing to sort of think about, and as a little exercise, see if you can find the derivative of 1 over x in general as a function. So pause this, take a minute to think about that, and then we'll run through it together. Okay, so what do? We have the limit as h goes to 0 of 1 over x plus h minus 1 over x, all divided by h. This is equal to the limit as h goes to 0. If I cross multiply this, this is going to be x minus x plus h divided by x times x plus h, all divided by h. Well, this is equal to the limit as h goes to 0 of negative h, I'm sorry, I wrote a negative x, but I meant a negative h, divided by hx times x plus h. These h's cancel, and now I can, as long as x is not equal to 0, I can find this by evaluation, and this is going to come out to be negative 1 over x squared, which is actually negative x to the minus 2 if we want to write it that way instead. So there we go. We found this derivative as a function. Okay, so like I said, we'll come back to thinking about this. We'll talk about like how do you take a look at a graph and sort of estimate the derivative? How do you recognize a graph of a derivative from a graph of a function? And all that kind of stuff. But for now, I want to stop this here. We've been going long enough, I think, and let me know if you have any questions.